Hi everyone, this is Sirush, and in this video I'll talk about ProlificDreamer work and mostly focus on variational score distillation that they proposed to generate 3D objects and scene from a text prompt with an impressive quality. I hope you enjoy it, and let's just see how it works. DreamFusion is the first fork that synthesizes 3D objects from the text that I have a YouTube video about it explaining how. However, as can be seen, they have the issue of oversaturation and oversmoothness, and in addition, as is stated in the discussion section of their paper, they have the issue of low diversity. And to give you a quick reminder of what this loss is in the DreamFusion work, we have this differentiable function g, our nerf model, that given its unique parameters theta that is learned, and a condition c that has to say where the camera is located, it should give us a 2D image output as if a 3D scene is captured from the specific camera. And to optimize the parameters theta to represent a new synthetic scene, they have proposed this STS loss that in a nutshell, they sample a noise, add it to the rendered image from the nerf model to have the noisy image xt, and have it as the input to our already trained denoiser in addition to time step t and camera over text prompt yc, and the denoiser has to predict some noise. And like most denoising diffusion objectives, the noise is compared with the original noise we sampled from, but this time instead of trying to optimize the weights of the denoiser, we minimize the loss by updating the theta that are weights of the rendering function g. So we can have this intuition that the denoiser already has a good image prior, right? A good image prior that can create a 2D scene from a text prompt given its noisy version. So the denoiser can be used as a teacher to guide the parameters of the rendering function theta towards a synthetic scene by rendering some imperfect garbage-like scene from different cameras each time that are x0 and making it noisy to get xt and denoising it back to have a better x0 and update theta with this better x0 iteratively. However, at the end of this training, which takes around half an hour using one 800 GPU, we only converge to a single theta parameter out of all possible theta parameters that can describe that scene. So here comes the motivation that we can say the theta parameters for a given prompt y comes from a distribution of all possible theta values, less denoted by big theta. Having this in mind, we can ask this question that what if instead learn to align the distribution of theta values with distribution of images generated by diffusion model given by the same prompt. And that is an interesting idea because instead of learning a single data point theta in a distribution of all possible theta values, we try instead to learn the big theta values that if we sample one from that distribution, it should give us the parameters of a nerf model that can render a 3D scene aligned with that text prompt. And although it is interesting, and I hope you also find it interesting, this is a super difficult task because learning a single data point takes about 30 minutes, let alone learning the whole distribution of data points. So here the paper comes and provides a solution for that question by proposing something called Variational Score Distilaltion or VDS. And to mathematically say what I just said earlier, we have this mu as our probability density function that given a text prompt y, it should give us theta values of a nerf model. And assuming that we have a nerf model that given its parameters theta and camera c gives us the image x0, we can write it in a probabilistic way like this, that given the camera c and text prompt y, it uses the probability density function mu to give us distribution of x0 values. And for our already trained diffusion model, we can define distribution p0 that says, given the view-dependent text prompt y, what are all the possible images x0 that the model can generate at time step t0. And for aligning these two distributions, we can define KL divergence to minimize the distance between these two sets of distributions and have a variational inference problem that tries to approximate a variational distribution q0 to be as much similar to our target distribution p0. But there is a challenge, and the challenge is that the p0 is complex and it's not easy to minimize the KL divergence just by applying this loss. And as a reason why, you can imagine p0 as a distribution of one-dimensional samples like this. In this figure, x-axis should denote all the different possible values that we can get in our one-dimensional space, and the y-axis should denote the probability density value of that region. What can be seen is that we have lots of high-density areas that are extremely sparse. This can be our p0 distribution and makes it difficult for us to learn variational distribution q0 to approximate this distribution. But luckily, we have our diffusion objective that we can leverage on. And based on diffusion objective, as we add noise, we get something like P1. And we can see that P1 is smoother than P0. and we add more noise and get P2 that is even smoother, and we do it over and over and over, and ultimately we should get P capital T that is close to a random normal distribution with zero mean and a unit variance. And since it is easier to learn a distribution that is closer to a standard Gaussian, they modify the training objective, and instead of minimizing this scale divergence at time step 0 that has sparse high density areas and difficult to optimize, they do it at different time steps and take average of this loss values over different time steps, which is kind of similar to STS loss, but now we are dealing with distributions instead. And to be a bit more detailed about this loss function, Q of t shows how we can derive noisy xt given camera C for viewpoint and text condition y. And we can start by Q0 that gives us x0 after the rendering and iteratively add noise to reach xt, and the noise is coming from the forward diffusion that we add a noise based on a predefined scheduler that we have. And for P of t, we start from a P0, which is generated image of the diffusion, x0 given the condition yc, and we iteratively add noise, which is the same noise as before, to make it noisy and reach x of t. And the job of this scale divergence is to match the distribution of all the xt's derived from our NERF model and then added by noise to all the xt's generated by a pre-trained 2D diffusion model that has the image prior. And it is weighted by WT, that is a unique weighting per each diffusion time step, as the middle time steps are more important than capital T, that is pure noise, or a T equals 0 that doesn't have any noise, and multiplied by sigma T over alpha T that are coming from the diffusion scheduler, and you have to watch the DreamFusion video if you're interested to see why we have this multiplication. But here comes the tricky part. To solve this problem and minimize this loss function, we have to learn this probabilistic density mu to be able to generate rendered images given camera C and text condition Y. And that can be done if we train another diffusion model to do that. But training another generative model for mu is expensive because it brings lots of computation and optimization complexity. So as a solution, the authors in this paper rely on particle-based variational inference. And to tell you briefly what that means, it's like defining a set of particles randomly distributed in the space, in our case the base of our NERF model, and our job is to move these particles in a way that when we look at them as a whole, they should represent the probability density mu star that we aim to get. And obviously, the more particles we have, the better we can describe this probability density, but at the cost of more computation. And this paper surprisingly shows that only 4 particles are enough to generate a good sample. And hopefully this idea makes sense, and now let's just see how this optimization works. To make this particle-based optimization happen, we can use Wasserstein gradient flow, and I believe Wasserstein means Waterstone in German, and buckle up because it is easy at first, but it gets a bit tricky as I go into the detail. What we have initially is a random distribution defined by randomly initialized particles, and what we are aiming to achieve is this mu star, or at least samples as if they are drawn from this mu star that should be high quality 3D objects aligned with the text. And to make this optimization happen, we can define an ODE path that points from the random distribution of particles to mu star. And if I get a sample in the middle of this ODE path, it should be a distribution not as perfect as mu star and not as random as what we initially had. And of course this ODE path is continuous, but we can have a continuous thing in computers, so we can define a set of intermediate distributions in our optimization step that we aim to start from the beginning, that is mu0, a random distribution, and go further and further and further until we reach mu infinity, assuming that we have infinitesimal number of this intermediate distribution, and that is our optimal mu star. So this paper denotes all its intermediate distributions as mu tau, and note that times denoted as tau are different than times t that we have in diffusion, so we denote it by tau instead. And to know how we can jump from mu tau to mu tau plus 1, that is one step distribution closer to our optimal mu star, we first sample particles theta 0 from the random noisy distribution we have, and once we reach theta tau and we want to go one step further, we define Wasserstein gradient like this giant equation. And to understand what this equation means, let's just briefly revisit the score functions in the diffusions. Assuming we have data samples coming from distributions like this, then we can define a score function as gradient of log probability that should give us directions as these arrows that you can see they are pointed towards high density areas of our space. So no matter where we are in the space, the score function should give us a direction that if we move in that direction, we should reach the high density area. And coming back to our equation, you can see that here again we are having the gradient of log probability of the pre-trained diffusion model, but multiplied by negative sigma t, which should be the opposite direction of the score function, or in other words, the noise prediction objective of the diffusion. And simply this equation says the noise that the pre-trained diffusion model predicts given the noisy image xt should be equal to the noise that another generative model q that we aim to achieve can predict, that as input it receives the camera and text separately, and if we can do such a thing, we can have a generative model q that given arbitrary text y and camera viewpoint c can generate the scene from a specific viewpoint, and by changing the c we can have it from different viewpoints, so we have a 3D object. But I already have told you that we have an issue, and learning this generative model Q is expensive. That was all the motivation behind why we are using this particle-based variational inference instead. And here comes the tricky part. Instead of our goal being to learn a perfect generative model Q, we change our goal to learn a better particles theta, such that we can generate a better rendered image x0 and therefore a better noisy input image xt. And even if we don't have so perfect generative model Q, by having a better theta values and a better input, we should better close the gap between the predicted noises. And building upon this intuition, the authors in the paper says either we train a small unit for Q or use a LoRa to fine-tune the pre-trained diffusion model P and have a weak generative model that can help this optimization happen. And to be more specific and tell you what's going on, the training of this weak generative model Q should happen each time before this optimization we have. And to do so, we use n theta parameters from n different nerf models, which is 4 in this fork, to render n different objects. Our goal is to make these n theta parameters better and better in each time step tau that we have in Wasserstein gradient flow. But before that, we need a helper generative model Q that has to be trained each time before this optimization, and that generative model can be optimized this way. Note that all we optimize here is phi, which is parameters of diffusion model that has to represent our weak helper model Q. And this diffusion model receives as input the noisy images after getting rendered from nerf model with parameters theta, and then adding noises, and is conditioned on time step t, camera c, and text prompt y. And like most of the diffusion models, it is penalized to predict the added noise. And after when we tune this helper generative model, we have our main optimization that we tune the particles theta, in our case the nerf parameters, by saying whatever the noise the helper generative model predicts as a noise should be equal to what our pre-trained teacher model predicts. But now, instead of tuning the helper function, we tune the parameters theta that serve as input to that helper generative model now. And we do these two sets of optimization alternatively, one after the other, to move these particles towards our optimal probability density mu star. And as you might have guessed till now, it should be slow. And although they have tried to mitigate the time complexity by learning the particles instead of the actual generative model that can generate for each sample, when you look at the paper, they say that the model that they have takes hours of time to generate, but they don't say how much. However, when you look at the follow-up work like VSD, they have shown that on a single 800 GPU, it takes 8 hours of time, while DreamFusion takes around 30 minutes. So only in the cases that if you want to generate a 3D object with high level of details and time is not your concern, then you can rely on this ProlificDreamer that uses variational score distillation. And yeah, that's all I wanted you to know about this work. Hope you enjoy it, and if you did, don't forget to like and subscribe. And until the next video, goodbye.